Okay, so just again to get basic understanding to Micah and you, how much comfortable are you with whole quantum measurement stuff, so that I can go over it depending on your understanding. Are you comfortable with quantum measurements? Do you understand, or understanding is still unclear a bit?
Not very clear. Yeah.
Okay. So just to iterate, we saw that there are 4 postulates of quantum mechanics. The first postulate tells you that how do we represent states? States are vectors in Hilbert space with norm being 1. The second we saw how do we combine multiple quantum systems. It was with tensor product. The third quantum postulate we saw was how state evolves in time. So if you have a state at time 0, how do you get a state at time t? It's just a unitary evolution. You multiply by a unitary operator to your initial state and you get the final state. And now we will see how do we extract information out of our system. That is, how do we perform measurements. Okay. And again, if any part is unclear, stop me, ask me questions, and if any terminology that I'm using you're unfamiliar with, stop me and ask me what does this word, this phrase means. Okay, so the fourth postulate, the measurement postulate, tells us that quantum measurements are described by a set m sub k measurement operators which satisfy the condition that the sum over all the measurement operators such that mk dagger mk is equals to identity. Initially, this condition might seem pretty arbitrary, but we will see that this condition again pops out from the need for all the probabilities to add up to 1. So first we will see very technical stuff, very arbitrary algebra, and then once we do a couple of examples, I think understanding would be more clear. So bear with the first technical stuff. So given a state psi, if you have a state psi, and if you do the measurement, your state psi becomes a state, let's say psi sub k, where your psi sub k state is given by m sub k psi under root p sub k with probability p sub k being psi mk dagger mk psi, which is nothing but the norm of mk psi squared. And you can see, since this is a norm, it's already greater than or equal to 0, which is the condition for probability. This quantity cannot be negative. So what does this mean? So if you have state psi, every measurement corresponds to a set of these mk operators. So let's say you have state psi and you in your lab you perform a measurement corresponding to set m0, m1, mk. operators. Then there can be k different outcomes. You can get state psi 0 with outcome 1 with probability p0. Same psi 1 with outcome let's say 0 with outcome 1 with probability p1, and you can have k different outcomes after your measurement. Okay, so what does these outcome mean exactly? So you can think that whatever your measurement apparatus you will set up to perform the measurement corresponding to these operators, then imagine a dial, you have a dial and it can point to one of the k locations. After measurement, the dial will move to one of the k possible positions, and depending on what you see, you will conclude that your state is psi 1. When you perform a measurement, you will never actually see the state psi 0 or psi k, whatever. You get the outcome on your measurement device, and depending on your outcome, then you imply that now my state must be psi 0. So for example, if we are measuring a qubit, let's say, so, and we have a device, so let's say we get the 0.5 voltage output, and then we say that, okay, now my state must be 0, or if I get plus 0.5 voltage output, my state must be 1. So these are the outcome 0, outcome 1. So the outcomes is what we physically observe in experiments. And from the outcome, we conclude, we infer that what my state now should be. So this is what we call as generalized measurement. This gives the general mathematical structure of how we represent measurements mathematically. So there are two categories the way you can measure a system. You can measure a state, or you can measure observables. And within measuring a state, then you have few special cases such as projective measurements, POVMs, and weak measurements. So all of these follow this mathematical basis. It's just that these are special cases of generalized measurement. That is, there are some extra conditions on these measurement operators, the set, which gives you different types of measurements. And one more thing, when we measure a state psi and it becomes state psi k, apparently this process is instantaneous. It takes zero time for this state to go from this to this, and which is why the measurement postulate is still one of the controversial postulates, that there are many debates around quantum measurements. Yeah.
The functions and all the content on the left side applies to all kinds of measurements, right?
Yes. This applies to all kinds of measurements.
Okay.
What these are like special cases of that.
Oh, okay.
Thank you. Yeah. This framework is what we call as generalized measurements.
This is general.
Yeah. Okay, now let's first see measuring observables. You will actually see that measuring observables has the same mathematical structure as projective measurements, essentially. Okay, so what is measuring an observable? So every Hermitian operator which satisfy this condition, that is, its conjugate transpose is same as the matrix itself. So these are Hermitian operators, and every Hermitian operator is a valid observable. But before we get into that, broadly speaking, what are observables? Observables are like properties of your system you can measure. For example, a spin of an electron along the x-axis, or spin of an electron along the z-axis. So you will have an observable corresponding to that, or position of an electron in space. You will have a Hermitian operator, an observable corresponding to that. And for like every quantum property, you have an observable corresponding to that. However, you might ask that what if I just make up some random Hermitian matrix? What does that correspond to? Then you can think of a random Hermitian matrix as you can always set up some apparatus in your lab such that the experiment that you will perform will correspond to that Hermitian operator, and that would be the observable you will be measuring. Okay, so what properties of Hermitian operator do we know? Do you guys know any properties of Hermitian operators? Hermitian operators in real space are where the A is A transpose, basically.
Yeah, have real eigenvalues.
They have real eigenvalues, yeah, that's correct. And there is one more important property. The eigenvectors of Hermitian matrix are orthonormal. Yeah. Okay. So how many of you know spectral theorem? Okay. So let me tell you what is spectral theorem. So if you have any matrix A, you can always represent that matrix as sum over its eigenvalues lambda i's and respective eigenvectors. Okay. So you can always represent every matrix like this, where lambda i's are the eigenvalues of your matrix and k is the eigenvector corresponding to the eigenvalue lambda. Let me call them k, my bad. Yeah. So lambda k is the eigenvalue and the vector k is the eigenvector corresponding to the eigenvalue, and then you take the outer product and you can sum over it. And this is the, yeah.
But this means it can be diagonalized.
Yep, exactly. In this basis, whatever these bases will form, it is diagonal. In the basis k, this operator will be a diagonal operator. Okay, so similarly, we can diagonalize this and we can write it like this: sum over lambda k, k. Okay, so we can represent every Hermitian operator like this. The special thing here is that these will be real and these will form an orthonormal basis, the eigenvectors k. So here our outcomes become the eigenvalues. More specifically, the distinct eigenvalues. Whatever the distinct eigenvalues are our measurement outcomes. And our measurement operators would be this, the outer product of eigenvectors. Okay, so let's check if what we have defined here satisfy the condition, because for these to be valid measurement operators, they need to satisfy this condition. So since now our mk operator is outer product of eigenvector kk, so if we sum over all k mk dagger mk, this will be sum over outer product k, and you can see that this will be 1 since it's dot product of a vector with itself, and since these are all norm 1, this is k sum over kk, and the property that we know that these are orthonormal and form a complete basis, this will be identity. So they do satisfy the initial condition. So now assume that we are given a state psi and then we measure the observable edge. So now basically the math will follow the mathematics that we have written over there. So your probability of getting the kth outcome means the lambda value lambda k. This will be what we have written there, psi mk dagger mk psi. But here our mk's are these, so this will be psi k psi, which is just the psi k square. Because this will be a complex number, this will be the conjugate of that complex number. So just the norm square. And now, what would be the post measurement state? So the post measurement state would be psi k upon getting the outcome k.
I think for the probability, it should be for phi and for k and cat phi. I think for the p.
What do you mean?
It's for pk.
Mhm.
The last result is that I think is for k and cat phi.
It doesn't matter since you are taking the
Just
norm
the
square. Yeah, so this, like I mentioned, so this will be a complex number z,
Yeah.
and this will be then the complex number z conjugate.
Yes.
So z conjugate is equals to z conjugate z.
Oh yes.
It's just complex numbers.
Yes.
Yeah.
Yes.
Okay, so the post measurement state would now be, if you can see, it was mk psi with normalization of under root pk. Our mk here are the outer product of eigenvectors kk psi, and this is our probability. So the root of this would be psi k. And if you know, again, this is a complex number, and then we are dividing with the norm of it. So if you have z, complex number z, and you are dividing with the norm z, do you know what this equals to?
Just unit vector z cap.
No, this won't be a vector. This is a complex number. A complex number divided by the norm one, the norm of this. This will be of the form e to the I theta. This will be a complex number with norm 1. Okay, so this we can write it as e to the I theta k. So now you can see that regardless of whatever our initial state was, after measuring an observable, we end up in one of the eigenstates of our observable. So whatever eigenvectors or eigenstates this H has, post measurement state would be one of these eigenstates. There are no other possibilities. It can only be eigenstates upon measuring this.
We don't know the theta here, right?
We can calculate theta from this.
Yeah.
But the point is here that this is a global phase. What this is a global phase. I think Professor covered global phases, right?
Yeah, you mentioned.
Yeah. So this thing doesn't correspond to anything physical. You cannot measure this. This is like something extra which comes up with the mathematical way we have structured everything. If you want to get rid of this, you would have to represent your state as not a vector in Hilbert space, but as a ray in projective Hilbert space. But for now, this is a global phase. We don't care, and our post measurement state is just K, which is the eigenstate of your observable. Any questions? Okay, so let's see a simple example for measuring an observable. So if you want to measure an electron along the axis positive z, the corresponding observable is poly z matrix. Okay, now let's write the spectral decomposition of this. You can check, double check if this is correct by doing the explicit math, but you will have eigenvalue +1, which will correspond to eigenvector 0. And you will have eigenvalue -1, which will correspond to eigenvector 1. Check if this works out. Do the explicit multiplication and check if you get z back.
Is it the situation that we measure the like quantum state in like z-axis in below sphere or like whatever else?
What do you mean? Yeah, this is an observable for measuring electron spin along the z-axis, the positive z-axis. Okay, so what outcomes we have here? The outcomes we have are +1 and -1. And what are our measurement operators? These are 0, 0 and 1, 1. So let's calculate the probabilities now. The probability of getting the outcome +1. Can somebody tell me how we will calculate this?
We don't know because we don't know the state to measure.
Yes. But assume state is psi, a general arbitrary state. Okay, so let's start with state psi. We are measuring this state psi, which is this. So how would we calculate this? It would be just again psi mk dagger mk psi, the general formula. But we know the measurement operators are these. So psi 0, 0 psi. And if you calculate this, you will find that your probability would be mod of a square. Similarly, if you do the probability for -1, it will be mod of P square.
How did you go from the Z matrix to its like the next line? You said we can verify it, but how do we go? If you are given a arbitrary
Okay,
matrix,
so the way you go is calculate the eigenvalues, calculate the eigenvectors, and then write it like this. So if I'm given matrix A, I will first calculate its eigenvalues lambda 1, lambda 2, lambda k. Then how you calculate the eigenvalues, do you know? Yeah, so then for each eigenvalues you calculate the eigenvector. Let's say lambda 1, lambda 2, lambda k. Now once you have all eigenvalues and all eigenvectors, if you just write it like sum over k, lambda k, outer product of the eigenvectors, you will always get the matrix back. This is the spectral, this is what we call as spectral decomposition. Where these eigenvalues we call it as the spectrum of the matrix.
For some cases, just like homework 2, the second question, the eigenvector is too complex. How is there an easier way for us to get a projector?
Yeah, there is. But as far as I recall, I don't remember what the question 2 exactly asked, but you never truly needed to explicitly calculate the projector. Yeah, you could have been a bit clever and made a clever argument without needing to actually calculate the projector. Yeah. You will see once I finish writing the solutions and upload the solutions.
Thank you.
Okay, and then the post measurement states. The post measurement state on outcome +1. If you calculate this, you will find it would be e to the I some number theta, real number theta 0, and the post measurement state on outcomes -1 would be same e to the some I 5 1. Okay, any questions so far? Okay, so now we have seen that how do we measure observables. Now let's see projective measurements. And as I said, the projective measurements and observables have similar structure, mathematical structure. Okay, so what is a projector? Do you know the properties of a projection matrix?
B squared is P.
Yeah. So P square is P. These are the projection operators. So now our measurement operators, the set of measurement operators will all be composed of such projectors. So now we have extra conditions on our measurement operators that they have to satisfy this. Along with this, there are more conditions that these projectors need to form an orthonormal set. So what is an orthonormal set? So if you multiply two different projectors, PK, PL, that should be 0. But if you multiply the same projector, PK, PK, you get the same projector back. And there is one more property of projectors that they are also Hermitian. So now let's say we are doing a measurement a projective measurement for projection with projection operator P0, P1, Pk. So how do we calculate the probability now again? The same formula, P sub k. Okay, now the notation might be a bit confusing because I'm using P for the probability as well and P for the projector. So understand from the context which P I am referring to. Okay, so now we know that our measurement operators are Pk. So now our post measure, the probability of kth outcome would be psi, Pk dagger, Pk, psi. But we know that the projectors are Hermitian. So this is nothing but just Pk. But we also know that the square of a projector is the projector. So this is the probability of getting the kth outcome when doing a projective measurement. Now, similarly, the post measurement states would be the same that we have described over there. Pk, if our initial state is psi, then psi and the root of the probability. We will get this state or the kth outcome with probability Pk.
So this is a post measurement state
Yes.
and not exactly the state corresponding to the eigenvalue. I mean the state before the measurement, exactly at the moment we measure it.
Mm-hmm. I didn't understand your question. So initially you have state psi,
Yes.
and then you perform a measurement which corresponds to these operators.
Yes.
Okay, so what's the question?
Okay, so the post measurement is just the psi collapsed after measurement.
Yes, but it's not. You can say it is collapsing, but that won't be the best terminology to use because these can be anything. These doesn't have to end up in the one of the basis states. They can be in a different state. So the state doesn't have to collapse to one of the possible states in the superposition. It can move a bit after a measurement.
Oh.
Yeah.
Thank you.
Yeah. The one important thing about projective measurements is that if you do repeated measurements, like if you measure, you get the kth outcome, then on this state, you again perform measurement corresponding to this. In case of projective measurements, the repeated measurements doesn't change the state. We can verify that. So initially we had the state psi, we measured it with a measurement corresponding to these operators, and we let's say got the outcome psi k. Now again we are performing measurement on state psi k. Okay, so what would be the state post measurement? Let's call it psi k prime, and how we define it? We define it with the projector pk prime and the initial state. But the initial state in our case is psi k with the probability. But the initial state is this. So it's pk psi pk prime pk. So if you see here, since the set is of orthonormal projectors, the multiplication of two different projectors will be 0. So the only term which survives, the only possible case is where this is also pk. So the k prime is also pk. So k prime is also k. So this will always be the kth outcome again. And that's why when we measure, when we do repeated measurements, we get the same outcome always in case of projective measurements.
Is it different from like projective measurement with like measuring the observables because like the probability formation was kind of like different? So are they like definitely different like measuring stuffs or like
No, not really, because if you remember, if you know that a outer product of any two vectors is always a projector. So this will always be a projector.
so when we measure like it with like observable with like along some axis, then we can like perceive it as a like projective measurement.
Yeah. The only difference is that the outcomes. And also we will discuss later the expectation values. We have expectation values with respect to measuring observables, but we generally don't say expectation values with respect to measuring a state. It's always with respect to measuring an observable.
Could you explain the last part again? I didn't get the point. So you just mean, do you mean that if we use the same measurements to the field, we will get the same outcome?
Okay, so what I mean is, if you measure state psi
Yes.
with doing a projective measurements to these operators,
Yes.
and let's say you get state some psi k. So here psi k would be a different state than psi.
Yes.
Now, if you perform measurement again, the same measurement, but on this state, we know that there are k different possibilities after a measurement. But if you are doing a repeated measurements, you will get the same state back again. It doesn't matter how many times you perform the measurement, you will always get the kth outcome that you initially got.
Oh, okay. Thank you.
Yeah, so repeated measurement doesn't change the state.
Yes.
But that's not true in case of generalized measurements or POVMs or weak measurements. Repeated measurements may give you different outcomes. This is a special property for projective measurements.
Oh,
Okay, so what are POVMs? So the full form, it's an acronym for positive operator valued measure. Okay, so before I start explaining POVMs, what is your understanding? Tell me your understanding for POVMs. It was the first question, right, for this homework. So what is your understanding for POVMs? Any idea? I mean, whatever you have understood.
Measurement thing, right?
What?
It's a partial measurement thing, right?
Not really. Partial measurement is when, let's say you have 3 qubits, but you're only measuring 1 qubit. That's a partial measurement.
The idea, I think, was we do not care about the outcome state, but we care about the outcome measurement, like the actual outcome. We don't care about the state. And that comes because you don't really have the MK in the final result,
Mhm.
but then you always have the under root of alpha I.
Mhm. Yeah. That's right. There are 2 main motivations for we describe POVMs. We describe projective measurements, but why do we need POVMs? So there are 2 main motivations as to why we need these now different measurements. The first is that there are some measurements which are we call as quantum demolition measurements. So there are 2 categories. One is quantum non-demolition measurement and one is quantum demolition measurement. Quantum demolition measurement is that when you measure a state, after measurement, state is gone. For example, imagine a photoelectric plate. You have photoelectric plate, electron hits it, it gets absorbed and it emits a light. We look at the light and conclude that electron was hit here, so we know that where electron hit. We perform the measurement, but after the measurement, there exists no electron. There is no wave function for that electron anymore. So it's what we call as quantum demolition measurement. For example, like our eyes. The photon is reflecting from that table, hitting my eye, gets absorbed by my eye, processed by my brain, and then I see that there is a table. But the photon is destroyed upon hitting my eye. So that's a destructive quantum demolition measurement. So there is no post-measurement state associated. The state just doesn't exist. State just doesn't exist anymore. So we generally describe POVMs for such cases. To explain second motivation. Okay, so before I explain the second motivation is basically what you guys did for your homework question 1. Can you guys explain? I have looked at almost everyone's homework and everyone has seemed to got the question 1 correct. Can you explain me what you guys did in question 1?
Measure in orthogonal, like linear, non-linear, like linear independent
Mm-hmm.
basis.
Mm-hmm. Yeah. Anyone else? What did you guys do in question 1 of this recent homework?
Construct a measurement set.
Mm-hmm. Yeah. But what was special about constructing that particular measurement? Why weren't you able to use projective measurement?
Because there was a like e to the n plus 1
Yeah.
state,
Yes.
like which is non-decidable state,
Mm-hmm.
something like non-categorized measurement operator.
Okay. So let me give you first technical aspect, and then we will see the motivation behind this. So everything follows the same. The only difference is that we don't have the post-measurement state, but we get the outcome k with some probability, and we have the probability. So in POVMs, there is extra condition that the MK dagger MK would be some operator EK, which is a positive operator. Then our normalization condition becomes that sum over k of ek should be identity. So the probability of getting the kth outcome would just then be this in this case. What is a positive operator? It's an operator with positive eigenvalues. That's it. The other way you can characterize positive operators is that for any vector 5, this value would be greater than or equal to 0.
As long as phi is not 0. Oh, well, yeah, it applies for all.
Yeah, for all. For every vector, this has to be
Yes,
equal to like greater than or equal to 0. Then your ek is positive. Okay, so let's see a kind of a game, I would say. So assume that the premise of this game is that I give you two possible states. You have to perform some measurement and tell me what state it is. The rules are, if you know the answer, it should be the correct answer. If you get it wrong, then you are out. Okay, so let's some math. So let's assume that we have two states, which are these psi1 and psi2, which are the state 0 and 1. Okay, assume that we play 100 rounds. 100 times I give you either psi1 or psi2 at random. You have to perform measurement and tell me what the state is. It's fine if you don't know. Okay, let's say if I give you a state, you say it's 0, it turns out to be 0. Okay, if I give you a state, you say 0, but if it was plus, then the game is over. And every time you guess it correctly, you get 1 point. But if you guess it wrong, the game is over, and you are allowed to say I don't know and go to the next round. Okay, and we are performing 100 rounds of this. Okay, so what measurement can you do to maximize your score here? What kind of measurements you can think of? Let's first go with the most naive intuition, the projective measurements. You either measure if it's a 0 or a 1. So let's say if we do the measurement correspond to P1, P0, P1, where these are the 0, 0 and 1, 1. Okay. So if we get the outcome 0, let's first discuss about the outcome 1. If we get the outcome 1, we know that the state has to be psi2. Why? Because what the plus state is 0 plus 1. And this is essentially the measurement in the 0 and 1 basis. So if we get outcome 1, which means our post measurement state is get 1, it means that our state cannot be psi1. So our state can only be psi2, then you can conclude, okay, it was psi2, you can tell me you get 1 point. But if you get outcome 0, now there is an issue. It can be psi1 as well, it could be psi2 as well, with half probability here. So if I'm truly giving you these states at random, and you perform these measurements, 25% of the times you will get outcome 1, and 75% of the times you will get outcome 0. 25% of the times you will say, okay, I got psi2, you would get 1 point, and 75% of the times you would have to say I don't know, because you don't know if it's psi1 or psi2, could be anything. So if we play 100 rounds, you will say get 25 points. So can we do better than this? And the answer is we can, using POVMs. And this is what you guys did in the homework 1. You had k different states which were not orthogonal to each other. The issue here is that the reason the projective measurement fails is that these are not orthogonal. If they were orthogonal, like if this was 1 then you can distinguish with 100%. But the issue here that they are not orthogonal, but they are not also linearly dependent. These states are also linearly independent. And that's what you essentially did in homework 2 question 1. That how do you distinguish between these states? How do you construct a measurement? So what you guys did were, I assume, you came up with some operators which were orthogonal to the other state. So the operator orthogonal to this for the plus would be the minus. So you take the outer product of minus. Let's take some coefficient for the satisfying the normalization condition. And the state orthogonal to this would be minus, and the state orthogonal to this would be 1. And then we have to satisfy the normalization condition. So we include I3, which would be identity minus E1 minus E2. Now, if you do the math, and you will do the math now, but I will just write out the results here. If you do the math, the probability of getting the outcome 1, if I had given you state psi 1, this would be 0. And so how would you calculate this, the probability? It's the same, so it would be psi 1 E1 psi 1 and when giving psi 1, I don't know why I wrote the other way, but yeah. Okay, yeah. So now if you measure this, you will get 0 because 1 is orthogonal to this. If you calculate the probability, this, you will find this to be 0. Similarly, if you get outcome 1, but I had sent you psi 2, then you calculate psi 2 E1 psi 2, and you would find this to be alpha over 2. Similarly, if you get outcome 2, which is this, the outcome number 2, and I had sent you state psi 1, how would you calculate the probability? Psi 1 E2 psi 1, and this would be, you will find to be alpha over 2. And if I had sent state psi 2 and you get outcome 2, the probability of this happening would be 0.
Is it different from like the one that we did on homework question 1, right?
No, this is exactly the same what you did on homework question 1. It's just that I'm restricting it, I'm taking some arbitrary state and restricting it to m equal to 2. Whatever the sub-index you had m,
Right.
I'm restricting it to m equal to 2.
But then, like, I think like E1 isn't the E1 has to be like alpha of like minus and minus, because what we constructed was like orthogonal to like size other than E1.
Yeah.
Like, so I think the like operators might have to be changed in order.
I mean, order is arbitrary, right?
Right. Okay.
The sub-indexes doesn't matter. It's just an arbitrary number.
Got it.
Yeah.
Okay.
For the E3, it also has to be a positive projector.
Yes, it has to be.
And how can we make sure that E1 plus E2 we do not over the identity? How can we make sure that we get the E3 to be a positive projector?
Well, it depends on E1 and E2, right?
Yeah.
So you have to check it algebraically depending on what is your choice of E1 and E2.
So maybe we can change the alpha Z factor to make it satisfy.
What?
Change the alpha, the factor of E1 and E2.
Oh, the alpha won't matter because the eigenvalue of E1 and E2 is not dependent on alpha.
Oh, yes. Yes.
It's just a scalar multiplier. Okay, so what if we get the outcome E3? So the problem here would be the outcome 3 because if you get the outcome 3, you won't be able to distinguish what state you get. So if you get outcome 1, the probability of the state being psi1 is 0. So you can always say that if you are getting outcome 1, I sent the psi2 state. If you get outcome 2 on your measurement, you know that state will never be psi2. So you can always say that if you get outcome 2, your state is psi1. And if you get outcome 3, you say I don't know. Go to the next round. And now we can choose the maximum value of alpha, and if you choose the maximum value of alpha, it would be with some complicated math, don't worry about it, but this will be the maximum value of alpha, and essentially this will occur 29%, this will occur 29%, and this will occur the remaining 42%. So initially with the projective measurement, out of 100 we were scoring 25, but now out of 100 we will be scoring 58 because on outcome 1 and 2 we can say with 100% certainty what state it is. Only on outcome 3 we say that I don't know. And this is useful for many applications, that when you are getting states which are not orthogonal to each other, you are still able to distinguish them up to some probability. So with 58% probability, we can distinguish them with certainty, but with 42% probability, we can't distinguish them. And this will be used in many cryptographic protocol when you will be doing quantum communications and looking at some quantum cryptographic protocols. Now, verify this, and verify any one of this statement. Do the actual math and see if you get what I'm claiming that you get. Those who are actually doing the calculations, let me know once you're done. And if you're stuck somewhere in the calculation, also let me know.
Do we usually put like E1 and E2 as like same alphas, or like is it the best practice, or like,
It depends on what you have to maximize. So for this, our goal was to maximize where we can distinguish between the states. But if your goal was to get more probability when the state is zero, so let's say your goal was when I send the state psi1, you want more probability to detect states zero at a loss of ability to detect state, loss in the probability of ability to detect psi2, and in that case then you will change those values. So it depends on the actual application or what protocol you are implementing.
I got one myself or two too.
Okay, nice. Okay, guys, then the last thing to discuss for today is just the expectation value and standard deviation for measuring an observable. So how do you generally calculate expectation value in general probability theory? It's the sum of outcome times its probability. So expectation value is always with respect to measuring a state. When we say expectation value, we always say what is expectation value of state psi for observable O, or like that. Because I saw many students making some mistakes where they don't consider state while calculating the expectation value in last homework. The expectation value is always with respect to some state psi. So let's say we are measuring observable A for state psi. So A corresponds to some property. We are measuring that property of our quantum system, which is in state psi. Okay. So expectation value of observable A given state psi. So there is you might encounter other notation, which is this. This means the same thing. It's an expectation value. And how do we calculate expectation value in probability theory? It's the sum over the outcome times the probability. And what are our outcomes here? Yes, the eigenvalues of our operator A. So let's say that our A has spectral decomposition lambda k and eigenvector ket k. So then we can calculate this as sum over k lambda k pk. We also know we can simplify this further, we know the probability of outcome k given a state psi. So this is where the dependence of state for expectation value comes in, because these probabilities are state dependent. So sum over k, lambda k, and as you know, just for simplicity to avoid writing k and k, these are also projection operators. So I will just call them capital Pk, let's say, for example. So I can write this as this. The probability is psi Pk psi. Now, this is just a scalar. This is not dependent on k. I can just move this inside. And what is this?
Expectation value.
No, what this thing is.
Expectation value.
No, this whole thing is the expectation value, right? I'm asking what's the thing inside the bracket. It's the spectral decomposition. It's the matrix A. It's the observable A again. And this is how we get the formula for expectation value. The expectation value for observable A for measuring state psi. This is how you calculate it. So you can calculate it two ways. One, if you are given an observable and a state, you can find its eigenvalues, find its eigenvectors, calculate the probabilities individually, and then use this formula to calculate it. And the other way would be this, the simpler one. So for example, if you are asked to calculate what is the expectation value of observable poly x given state 0. So this would be just 0 x 0, which is 0.
For the state, is it usually like a Bell state kind of thing in the question? State
It,
side?
it can be anything. It doesn't have to be a Bell state. It can be anything. Your system can be any state.
Right.
So
I mean, but for like calculation simplicity, probably like during exams,
mhm.
maybe like a Bell state would be most probably like a fair one to use to calculate.
No. So whenever you are calculating an expectation value, you will know the state to choose. You will be given a state. When talking about purely from exam or problem solving perspective, whenever you will encounter expectation value, you will always be given what state you are supposed to calculate. You are not supposed to choose a random state.
Well, oh yeah, I know.
Then I don't get your question.
I mean, can you give an example of like a computable side? Like
What do you mean?
like what could be a possible state for the side that we can like actually calculate? Like
What do you mean by state for a psi?
isn't side the state that we're
Yeah.
doing?
I mean, this is the example, right?
Right. I mean, okay, so it's just cat 0 like usually, or cat 1 or cat plus or kind of cat minus.
It depends. I mean, it depends. You can be given literally any state. I mean, you can have a question like you have state. Let's say this. Whatever A, B, C, D. It could be any arbitrary, and then you will be asked to calculate the expectation value of this for observable Z tensor X. So what you do is just sandwich this between psi and psi, calculate this 4x4 matrix, you have a 4x4 vector, and you get a number. That's it. There is one more thing. I don't think so. You might encounter this, but I will just state it. Like we have expectation value. There is another statistical quantity, standard deviation. So it is usually denoted as delta of A for observable A. So standard deviation for measuring observable A for a given state psi. This is just under root of the observable square expectation value minus the expectation value squared. So this is just under root psi of A square psi minus psi A psi square. So when you are defining quantum cryptography protocol and you want to know what are the asymptotic rates you can achieve, then generally you use these quantities practically to calculate what's the performance of my protocol or what's the average outcome. That's when you use this. Okay. The one mistake that a lot of people made and a lot of people asked me about in previous homework was regarding the outcomes, where you were asked to differentiate between the measurement MA tensor MA and measuring the observable A tensor A. Are you clear about that, or do you want me to discuss that?
No, let's discuss, I think.
Okay. So let's first talk about measuring A tensor A. Measuring observable A tensor A. So as you know, what do we know about observable? It's the distinct eigenvalues corresponds to different outcomes. Okay. Now, for sake of simplicity, I would just use poly Z here, but in the notes you will see for argument for the general case. So, what is Z tensor Z? Can anybody tell me the matrix?
So that's one.
Okay. What are its eigenvalues? 1 minus 1 minus 1, 1. It has 4 eigenvalues. But how many distinct eigenvalues it has? Yeah, 1 and minus 1. So when you measure this, the outcome, the possible outcomes you can have would be only 2. The other way you can approach this is find the spectral decomposition of this. If you find the spectral decomposition of this, you will find that Z tensor Z is with eigenvalue plus 1, we have state 0, 0, plus with eigenvalue minus 1, we have state 0, 1. With eigenvalue minus 1, we have state 1, 0. And with eigenvalue plus 1, we have state 1, 1. So, we can now write this as plus 1, 0, 0, plus 1, 1, plus minus 1, 0, 1, plus 1, 0. Now, you can see it is in the form of sum over lambda k outer product kk. Well, my bad. These all should be outer products. Let me rewrite it again. Or do you understand? I mean, just these will be all outer products. It will be outer product 0, 0, 0, 0, 0 1 outer product 0 1, 1 0 outer product 1 0, and 1 1 outer product 1 1. 1 0 0 1. So now this is in the form of lambda k or outer product k and k. So when there is a degeneracy, so this is what we call as degenerate eigenvalues. So this is a degeneracy, and now our projector is two-dimensional projector. Initially it was just the outer product of single ket, but now we have summation here. It's two-dimensional projector now. So here our lambda k's are +1, -1, and the measurement operators are 0 0 +1 1, which corresponds to the eigenvalue +1, and the second one is outer product of 0 1 and 1 0. This is our set of measurement operators for measuring observable Z tensor Z. Two outcomes, two measurement operators. However, if you are measuring, let's say you are performing some measurement MA, which corresponds to a projective measurement with projector P0, P1. When I say measurement MA, tensor MA, it means that I'm performing this measurement on first qubit followed by the measurement on the second qubit. So in this case, what happens is the total set of measurement operators is just the all possible tensor product of these two. So this has these projectors, this has these projectors. So the all possible tensor product would be P0, P0, P0 tensor P1, P1 tensor P0, and P1 tensor P1. And as you can see, now we have 4 different outcomes here, because the difference here is here you are measuring a combined property of two systems. When you are measuring an observable like this, so for this particular case, it's like you are measuring both the qubits along the positive z direction, and then you can only have 2 outcomes. Whereas here you are doing some first projective measurement on 1 qubit, then a projective measurement on second qubit, and then you can have 4 different possibilities. This was the most asked question for the previous homework. Okay, so maybe let's do a quick 2-3 questions regarding expectation value, and then I guess if you have any questions, otherwise that's it for the day. So the first, calculate the expectation value of measuring observable Z given state 1. Calculate the expectation value of observable Z given state plus. And lastly, calculate the expectation value of observable X tensor Z given state psi, where state psi is your Bell state. Let me know when you guys are done.
You will get too close.
Are you stuck somewhere? Okay, so let's quickly calculate this. If you remember the formula, the expectation value is just sandwich the observable between the bra and the ket of your state. So z acting on 1 gives you -1, and this is just -1. Z acting on plus, z acting on plus becomes minus. Plus and minus states are orthogonal, so this is 0. Yeah.
Why is the inner product of plus minus 0?
What do you mean?
Inner product,
Yeah, inner product of plus and minus is 0. It's not. Yeah, inner product of plus and minus is 0.
how do you, is there a matrix
Yeah.
representation?
Yeah. I mean, what is the bra plus? Bra plus is just the row vector this, and the bra minus is, and then you do it 1 minus 1 half, which is 0.
Yeah.
What is plus state? It's just this vector. Similarly for minus, you just have a minus sign here and a minus here. Okay, how do you do this? You can do it here also explicitly without writing matrices, but that might become tedious. So let's do explicit multiplication. So if you represent this as a vector, this it would be a 4 by 1 matrix. So it would be 1 0 0 1 multiplied by √2. I will write √2 outside. Then let me write it like this first. So this is psi x tends as z get psi. So what is bra psi? It is 1 over √2. The column vector 1 0 0 1. What is x tends as z? It is 1 0 0 minus 1 1 0 0 minus 1 0, and then same 1 over √2 1 0 0 1, and then you just do matrix vector multiplication. Did you solve this? What's the answer? What is the answer you get? What?
Minus 1 over 2.
No, you get 0. I mean, unless I have made a mistake in my own calculation, you could be right, but I think it should be 0.
Thank you.
Okay, so just to recap before we leave, what did we do today? So all of the measurements are described by this mathematical framework, which we call as generalized measurement. Every measurement corresponds to a set of measurement operators, which is MK, and they have to satisfy this condition to be a valid measurement. You have a post-measurement state, which is given by this, and you get this post-measurement state with some probability pk. So on measuring a state, on performing a measurement corresponding to the measurement operators mk, you will have k different possible outcomes upon measurement, where each of them will occur with some probability pk. And what are these outcomes? These outcomes could be anything. Like for example, the outcome 1 means I get 0.2 voltage. Outcome 2 means I see 0.4 voltage on my display or whatever. So these are the outcomes. Then we saw measuring an observable. What is measuring an observable? It's a property of a system that we measure. And every Hermitian operator is a valid observable. And then you have same mathematics for that. Then we saw projective measurements where we had more restrictions on these measurement operators, where these measurement operators had to be projection operators and they all together had to form a set of orthonormal projectors, which is that the multiplication of two different projection operators has to be 0 and the sum of all projectors should be identity. Then we saw the POVMs. Why do we need POVMs? The main idea is we can distinguish states which are not orthogonal. What you guys did in homework 2 question 1. And then we saw the expectation values for the observables. And yeah, that's it for today. If you have any questions, ask me or you guys are feel free to leave.